Oh, thank you. Hopefully this one will be interesting as well. So what I wanted to talk about is IOs on FPGA, more specifically on the iCE40, because I find that sometimes people are confused, and I also wanted to show exactly how I push the I/O of the iCE40 to I/O speed, like for the IPRAM and stuff like that. So I'll start with just the basics of I/O timing analysis with examples on the iCE40. I'm just gonna look at, for instance, interfacing SPI chip, and um, and then we move to I/O speed and how we can basically implement like high speed SerDes and input and output SerDes on the iCE40, which is what I used for the IPRAM that I showed in previous streams. So let's get started. The first thing to understand about I/O timing is kind of the parameters of synchronous logic. So if you have a register which has a given clock, it has a input data and a output data, classic flip-flop, right? And the critical parameters are going to be the setup time, the hold time, that's for input, and for the output you essentially have the clock to out and the clock to out minimum value. It's kind of the 3 or 4 parameters depending on how you count clock to out as 1 or 2 parameters. So I'm going to explain what those are. So let me draw the clock signal. Let's draw a clock. Right. And that's a positive edge flip-flop, which means it samples data on its rising edge. And so that's the input data. So what I named D. So you have some data here. Okay, and then that's invalid, and that's invalid. And then you have the output, which is Q, which is gonna be so this would be the previous output. This becomes invalid. I'm gonna explain what the different zones are in an instant. I'm just doing the drawing. Hey, hi Peter. Oh yeah, I need to update the stream info. Does that work live? Like, I have no idea. Like iCE40 IO timing, and let's go with that. Yeah, it seems like it updated it, I think. Yeah, I saw the edit stream info thing. Yeah, exactly, the stream manager. Yeah, it changed. Thanks. Thanks for reminding me. Yeah, that can be useful. So the input parameters. So the setup time is how much in advance the data need to be present. So if that's the clock edge, what we consider to be the clock edge, That's the setup time. So you need to present the data at the input of a flip-flop before a certain time before, so that it's correctly captured. And then after the clock edge, you might need to maintain that data some amount of time after the clock edge. That's called the hold time. Now, that's the kind of typical thing is you have a positive setup and a positive hold. Now, those can actually have negative values. And a negative setup would mean that the data is actually required after the clock edge, and that's when you have different delay on the clock and edge net and stuff like that. But that's for what we consider positive setup and positive and hold time. When we encounter negative value, I'll go and re-explain that. So the clock to out is how much after the clock edge the valid data shows up on the output. So that's what we consider to be the clock to out delay. So once the clock edge happens, it's going to take some time for the flip-flop to actually switch its output to whatever the input was, right? That's clock to out. And then another value, it's like the clock to out min. Sometimes the flip-flop will actually guarantee that it won't switch value before a certain time. So after the clock edge, that's the clock edge, and then up till here, the old data is still present, and the flip-flop guarantees that it's still present. And that's useful because if the next flip-flop has a hold time, well, obviously it's very practical that the flip-flop just before doesn't switch instantly, right? And so you have like an invalid period between the two, where the data at the output of the flip-flop is indeterminate. So that was just like a quick reminder about how synchronous logic works and the terms I'm going to use in this stream in explaining the various things. I should say, if you have any question or if something isn't clear, don't hesitate. I'll try to look at the chat periodically, because sometimes I might not be very clear, or I might go fast over something or whatever. So let's look at I/O in FPGAs specifically. So we have some logic. So let's say that that's our FPGA, and what's inside the FPGA, and this is the world, which is outside the FPGA, right? And at some point we want to exchange data between the two. And we do that through pins and I/O pads, right? So far, it's pretty clear. Now, just as signals don't go instantly from one flip-flop to the next flip-flop inside the FPGA, you have a certain delay there from the net and from the clock to out from that flip-flop and the setup time from that flip-flop. It actually takes time also for a signal to go from an internal flip-flop through the I/O buffers, because at some point here you have a buffer that's going to convert from the V core to the output voltage, and to actually appear outside of the FPGA on the pad, right? And same thing for inputs. Like if you have an input that's generated by some chip. Here we're going to take an example of a SPI chip. It takes some time from the signal from the SPI chip to go to the pad, and then from the pad go through the input buffer and actually appear on a net inside your FPGA to be sampled by some flip-flop. So that's the basics of the problem we're trying to solve. Now, you don't always have to solve that problem because if you're working with something like a UART or something, it doesn't really matter. I tend to categorize like the kind of interaction with the world in like 4 categories, I think. I'm trying to remember, but yeah, 4. The very slow, you know, something like I2C, UART, you know, that's like 400 kilohertz. UART, you know, you might get like a 1 megabaud UART. That's basically DC for the FPGA, right? UART is even asynchronous, so there's no clock. So at that point, you don't have to take too much care. I mean, if you do some asynchronous sampling, you might need a dual register in the FPGA to avoid metastability, but that's a distinct thing from I/O timing. That's something completely different, and that's outside the scope of what I'm talking about here. Then you have the thing that, you know, faster, but you can usually get away with sampling on the other edge or stuff like that, and that would be like typically like SPI at, you know, less than 10 megahertz or something like that. I think I2S would also be in that kind of frequency range. I mean, that kind of relatively slow interface where the kind of delays you have between the inside and the outside of the FPGA is a lot smaller than your clock period. You know, the kind of delay we're going to be talking about here, they're like in the 10, 15 nanoseconds, possibly, something like that, which mean, you know, if you have a 10 megahertz clock, you have a 100 nanosecond clock period, which means the 15 nanosecond delay between the inside and the outside of the FPGA doesn't matter too much. You don't have to worry too much about it. Usually, just by sampling on the rising or on the falling edge, one of the two will work, and you can be pretty sure that you're well within the timing. And I think a lot of people actually consider IOs to be like, I mean, a lot of projects that I see in FPGA by kind of people that just started working with FPGA, they work with one of those two kind of IOs basically, where they don't have to worry too much about the IO timing. Then we have the third kind of IO, which would be something like what we're going to be talking about here, like SPI, like, you know, at 50 to 100 megahertz. And in sort of in this, yeah, SDRAM would be the same category actually. And here you do definitely have to worry about the timing, but you can do it in a kind of in a static way, which means it's essentially like a either analysis by the tool or by yourself, you know, pen on paper, drawing the different timing and ensuring by design that the IO timing are going to be met and that everything is going to work fine. Then the next category up would be something like hyper RAM. You know, I'm talking upper RAM, you know, at the maximum frequency, you know, like 100 to 160 megahertz DDR. Then pretty much all the DDR, you know, like DDR3 and stuff like that. Those, you do need to make a static analysis, but that's not enough, because the kind of delays you have between the inside and the outside of the FPGA have too much variation that you have no idea when you're going to need to sample your data for the input and stuff like that. And so those actually have dynamic training. So what that means is that, like, at boot up, your FPGA or your PC, like the DDR on your PC, it doesn't actually know the delays, the various IO delays on the board and between the CPU and the RAM and stuff like that, and it basically dynamically tries different delays and tries to find one that works, basically. Like, it's a bit simplified, but that's essentially the idea. That's what's called memory training for DDR and stuff like that. You actually have this, like, if you go to very high speed, like eMMC or micro SD at the higher frequency, you know, more than 100 megahertz, you can actually get retraining for those kind of memory as well. Okay, I said there was 4 categories, and there is actually a 5th one, which is all the gigabit SATA stuff, you know, like PCI Express, USB 3 and stuff like that. Like, you don't have, you don't even have a clock signal transported along of one. You can have one, but you don't necessarily have a clock signal transferred along with the data. It's self-encoded data with like 8-bit to 10-bit stuff like that, and you have like a clock recovery and stuff like that. That's a completely different way of transferring information, and we will definitely not talk about that here because you pretty much can't do that on iCE40, right? Yeah, self-clock data, exactly. Yeah. Although, I mean, technically, you can have some self-clocked data, like E1, for instance, the old, E1 T1 line. You know, they're self-clocked data, and yeah, technically you do have clock recovery, but you can do them in the iCE40 because they're slow enough. They're like 1 megahertz. Here, I'm really talking about the gigabit thing where you basically need an analog PLL with dedicated block in the FPGA to do clock recovery because you can't fake it basically, right? But yeah, they are self-clock data and at a sufficiently high rate that the FPGA can't do the clock recovery manually, I'd say. So what we're going to talk about here is essentially those two things, static and dynamic training. And I'm just going to start with the static one, talking about OSPI chip. Now, something else to know is that because, as you can see here, right, the delays between a flip-flop inside the FPGA and the outside is going to be a factor of the I/O buffer, but it could also vary depending on where your signal comes from. Yeah, that's kind of the how FPGA work. Like if you have your flip-flop very close to the I/O or very far, the signal would take a different time to get from that flip-flop to the outside. So the solution for that, and that's the only solution we're gonna, exactly, all the routing delays and stuff like that. Here, we're only going to talk about using the flip-flops that are inside the I/O blocks. So if you, let me actually open the I/O block diagram of the iCE40. I think that would be useful. Do I have? Let me. Hello. Are you kidding me? 53 kilobytes per second? Come on, lattice. Okay, let me see if I have a copy of it on my laptop. This is just ridiculous. Okay, yeah, it's kind of hit or miss. Sometimes it works fine, and then sometimes not so much, right? So I have this is gonna be this PDF might not be displayed correctly. Well, yeah. Indeed, it is not. What? Ah, wait. Sorry about that. I just small technical difficulty with having the temporary directory being full. SBIO. Okay. So that's the schematic for the I/O block of the iCE40, and as you can see, there are actually built-in flip-flops both for the input path. So these two flip-flops are used to capture data from the outside to the inside. You can see the paths here, 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 and then wait, what the hell? Is there a loop in that schematic? Oh wait, no, never mind. So this. Well, yeah, but you can actually create a loop, right? This. Okay, no, never mind. I mean, you can do this, and then this goes to those two flip-flops. Okay, so, and you have the same for the output. You have these two flip-flops. You have two flip-flops because you can act on the rising and falling edge for DDR things. Oh, thank you. And so we're gonna focus on using those because the delays from those flip-flops to the pads and from the pads to those flip-flops is constant. It's not gonna vary. Basically, it's fixed just by the architecture of the iCE40 itself, basically. Because if you use directly flip-flop from inside the FPGA, then you can have variable delay depending on when your flip-flop is, and that's pretty much a random, unless you fix it manually, and we'll talk about that at some point. The delay are gonna vary randomly depending on when you rebuild your FPGA, because it's a random process, right? Use the IOB as part of the clock domain crossing? You mean from the outside to the... It's not really a clock domain crossing from the inside to the outside, but... Or you mean from the outside to the inside, or... But yeah, you need to use those to have consistent timing, because else you might find that you generate your bit stream, it works, then you do some change that are completely unrelated, regenerate. Next PNR places those flip-flops at some other point in the design, which completely changes your timing from the inside to the outside world, and suddenly your thing doesn't work, and you don't know why. So using the IOB flip-flops is the best way to have consistency between builds. Now, being consistent doesn't mean it's gonna work. It just means it's gonna be consistent. So it's either gonna work all the time, or it's just gonna fail all the time, right? It doesn't mean it's gonna work. You still need to check that the timing are correct. Sorry, Firefox crashed. I don't know why. Whatever. So that's what we're gonna work on now. Now, the unfortunate thing is that the open tools basically don't support I/O timing analysis at all. Like, Next PNR can't tell you how much time the flip-flop here is gonna take to put the data on the pad, and it can't tell you how much time, like the input flip-flop, like what's the setup time is gonna be to the pad, stuff like that. All of these, those paths are just not analyzed by NextPNR at all, which means you can't constrain them, and you can't check them with the tools, with the open tools. That's kind of the unfortunate thing. So what I actually have is that I use the proprietary tools, and I made myself like a simplified table of the various parameters of the I/O registers. So I know that the I/O register need have a clock to out of 3.1 nanoseconds. Actually, those are the typical timing, right? It has a minimum clock to out of 2.8, and setup time requirement of 3 nanoseconds and a hold time of minus 0.4 nanoseconds. So here, as I said, you can have negative hold time, and that means that you can actually change the data before the clock edge happens. I'll draw a diagram later on that shows that negative hold time. Now those values, as I said, are typical, and I took kind of several. I'm gonna explain that. Several simplification that will be valid in most cases, at least in the iCE40. So the simplification I took is that the clock edge, so obviously your various flip-flops at various places in the FPGA, including in the I/O block, they all connect to the same clock, right? So everything is connected to the same clock. We just assume one clock domain here, and they all connect to the same clock. But that's a huge net that needs to be distributed everywhere in the FPGA, and having a certain physical size, the clock edge doesn't happen absolutely everywhere at the exact same instant. It also doesn't happen. The various flip-flops are also not entirely triggered at the same time, depending if it's a rising edge or a falling edge. But which the distribution here, we're just gonna ignore, because the FPGA has global networks that ensure that the skew is relatively small. In the iCE40, even the official tools actually ignore it for the most part, because the FPGA is so small and the global network does a pretty good job. Now, in a larger FPGA, like a large Kintex 7 or something, then you can actually have substantial skew, of like 1-2 nanoseconds before a different point in the FPGA of where the clock arrives. And the way you can sort of forget about that from an I/O standpoint is that if you're talking to a device, you try to have all its I/O in the same FPGA I/O bank, right? FPGA have different I/O banks. The iCE40 has 3, but really only 2. You have one that's on the top and one that's on the bottom of the FPGA. And within an I/O bank, you can be pretty much guaranteed that the clock skew is minimal, and you can ignore it for all purposes here. As I said, the other thing is, so we are speaking of very complex propagation delay. Well, they're not that complex. We're simplifying them to something we can understand, to something we can kind of comprehend, I'll say. But they're really not that complex. I mean, the clock takes a certain times to get from wherever it's generated, like a PLL or something, into the actual flip-flops at various places. And then that flip-flop is going to take a certain time to go from there to there. So it's really only like 2 values or three, 4 values. I'll get to the example soon, which hopefully will make things a little clearer. So as I said, the other simplification we're going to take is that the FPGA and the registers and stuff like that, they all act symmetrically compared to rising and falling edge. That's not the case. In practice, there can be some variation. Here, we're just going to ignore them, because they're relatively small, and if you take the average value between the two, you don't have that much deviation. And finally, here, I did put a range. I said the nominal value is 3.1, but I put a range between 2.6 and 3.6 is because it depends on if you're considering the best case timing or the worst case timing or the typical timing. Usually I'll do the analysis with the typical timing and then look so that I have enough margin that I feel comfortable that it's gonna work in the other cases. In theory, you'd need actually to run the analysis we're gonna do, run it 3 times. Yeah. And okay, so I think that's pretty much setting all the setup for the example. And so we're going to look at talking to SPI flash. Actually, no, we're going to look at talking at both SPI flash and at the same time a PSRAM. They're both going to be on the same SPI bus, which means that we need to meet the timing for both with one circuit, right? The same circuit has to meet the timing for both the flash and the PSRAM. So let's have a look at those chips, right? So the flash is going to be, that seems perfect. And the PSRAM is the LY64000 something? No? What is it? LY68L64000. Yeah, but I want the, okay, yeah, we can open that. So, we need to find the AC electrical characteristics. Okay, so we have our nice timing diagram. Let's try to find the equivalent in this datasheet. Come on, it has to have some timing parameters. Okay, yeah. Okay, it doesn't have a nice diagram, but it has the actual numbers, so that's good enough. So we're gonna look, let me, no, that's not what I wanted to do. Shit. How do I? Oh. Okay. There we go. Perfect. So first we're going to talk about the output. Sometimes that's all you have to care about is the output. Like when you drive like the LED panels, for instance, you don't have any input signals, you only have outputs, right? So we're gonna start with the output because well, really it's the easiest thing. So the output from the FPGA to the SPI chip. So we have our FPGA, and we're gonna consider two signals. The clock signal that's I'm gonna name that SPI clock, which is sent, and then we have a data bit. I mean, SPI can have 4 data bits or 2 data bits. It doesn't matter. The timing are the same, so it's a data bit, whatever data bit is related to that. So let's look at this data sheet because it's the most precise one. And so, of course, the output for the FPGA is the input of the flash, obviously. And so we have the SPI clock here, and then we have TDVCH. And TDVCH TCHDX. So yeah, so these are the two values, which yeah, I don't know why they named it that way, because hold time and setup time are much more common names or whatever. So you have a setup time and a hold time, just normal stuff, right? And they are hold time of 3 nanoseconds and setup time of 2 nanoseconds. So that means that if we have our SPI clock rising like this, that's the data bit that we're trying to send to the flash. We need to set it up 2 nanoseconds before, and it needs to stay valid for at least 3 nanoseconds after our clock edge. So far, so good. Now let's check the PSRAM so that we meet its timing as well. So it has a setup time of 2.5 nanoseconds and a hold time of 2. So there's a slightly more setup time and slightly less hold time. So we need to cover both at the same time, which means that here instead of 2.2 nanoseconds, I'm just gonna set 3 nanoseconds as well, so that those timings would be good for the PSRAM and for the flash at the same time. Okay. So that's a fairly common type of timing that you're going to try to generate with the FPGA, is basically generate the rising clock edge in the middle of the data valid window here. And the way to do that is to use a DDR output on for the clock. So I'm just gonna draw not what I wanted to do. Yeah. I'm just gonna draw the clock inside the FPGA. So that's the clock, the master system clock of your system on chip or whatever, right? Let me draw that one. Okay, something like this. I'm gonna name that system clock. Okay. So if we go back to our little this thing, We know the FPGA clock to out is 3.1 nanoseconds. Oh yeah, sorry, I didn't specify, but let's say that we're trying to run our flash at 100 megahertz. So our clock period here, that's 10 nanoseconds. So we're going to use an IO register to output the data bit, and we're going to draw that now. So we have our data bits, and we use a simple IO register, which means that 3 nanoseconds after the... How are you drawing the diagrams? So I'm using this thing. Like that tablet, well, the version 1, because the version 2 isn't out yet, and it runs Linux, and I'm running custom software on the tablet itself that's streaming what I'm drawing, basically. So like I have the tablet I'm drawing, and it's just streaming it on my PC. So 3 nanoseconds after the rising clock edge inside the FPGA. So we're going to reference everything to our clock inside the FPGA. That's going to be our timing reference. So 3 nanoseconds after, so that's be roughly here, our data is going to appear on the output. And it's only going to change, well, somewhere around here, let's say a little before, because that's the clock to on min, so let's say here. So we have something like this. That's invalid data. So that's data out. So that's sort of what it would look like, right? That's if we use a register on the FPGA to output data, that's where our bits are gonna arrive. It's 3 nanoseconds after the rising clock edge. So that means that now we need to generate a rising edge somewhere around in that period, so that we meet our 3 nanosecond window from the flash. So the usual way of outputting a clock from inside the FPGA to the outside is to use a DDR output register, which takes 2 inputs, one for the what to output on the rising edge and what to output on the falling edge. And so here on the rising edge, we're going to output 0, and on the falling edge, we're going to output 1. So that means 3 nanoseconds after our sys clock happens, because it's still an IO register, it might be a DDR1, so it switches 2 times per cycle, but it still has the same delay. Our SPI clock is going to output 0. So this, and then 3 nanoseconds after the rising edge here, we're going to generate a rising edge, because we're outputting 1. Here. Right, so we have this. Yes. And so the rising edge here is 3 nanoseconds after the falling edge. And so as I said, the outputs are rather easy because just by design itself, we exploited the fact that the delays from the flip-flops to the outside are kind of, they're constant. Like for all IOs, they're going to be the same, or you can consider them to be the same. And we use the fact that we have a DDR output register that can output data on both the rising and the falling edge. And so we use the falling edge kind of as a midpoint so that we generated a rising edge for our output clock, the SPI clock, right in the middle of our data valid window. And so if we actually look at the numbers, so if that's 10 nanoseconds, that means that this is 2 nanoseconds and 3 nanoseconds, which means we actually have a setup time here of 5 nanoseconds, right? And we have a hold time which is slightly smaller than 5 nanoseconds because we have the small invalid window here. If we go back and look at our timing data, we have the clock to out min is 2.8 nanoseconds. So our small invalid window is only, so this small thing is the difference between the clock to out min and the clock to out, and it's only 300 picoseconds. It's 0.3, which means here we actually have a hold time of 4.7 nanoseconds. And so we needed 3 and 3, we have 5 and 4.7, so we're easily meeting the timing requirement, the input timing requirement of our flash, and we can be sure that the flash is going to be able to read our command 100% of the time, all the time. Now, that pretty much works for any kind of output. Like every time you need to output a signal, you can ensure that kind of margin just by design. If you look at the similar, that there isn't a simpler mode for this. Well, I mean, the other thing you can do is instead of using the DDR output mode is that you output a SPI clock that's half the frequency of your system clock, of your FPGA clock. But then you need to run, that would mean that you need to run your entire logic at twice the speed that you would need, right? So that's kind of wasting your clock, if you wish. Now, there are, that trick only works if your data here is simple data rate, right? Because I use the DDR mode to kind of put somewhere in the middle. The alternative to that, there are two possible alternatives. I mean, there's an infinite possibility, but the two common ones, alternative to that, if you needed to output DDR data out, well, then you can't place the edge in the middle, right? So what you can do is use a different clock domain to generate your clock, and instead of feeding it the same clock as you feed the data, you use the PLL to generate a clock that's 90 degrees out of phase. On the iCE40, it's a bit annoying because the PLL is kind of limited and you need it potentially for other things and stuff like that. But in like the ECP5, stuff like that, like generating a 90-degree out of phase clock is something that's fairly common. That's one other option. And another one is just not possible on the iCE40 at all, but some FPGAs, you have the IO registers. Here you have the output driver and the pad. And right in the middle, you have a programmable output delay, which you can actually set, from like 0 to maybe 2 nanoseconds or something, which allow you to shift your edge by whatever value you want. It's not especially calibrated and stuff like that, but it's used, for instance, in AGMII, like the gigabit interface, stuff like that. That's something you could use. The ECP5 has that. So if you want an example of using the O delay, you can look at the RGMII phi in LightX. The light ETH phi uses that for the transmit side timing, the output delay block. If you want an example of the 90-degree phase clock, you can look at in the iCE40 playground, in my iCE40 playground repository. There is support for pushing data through a single PMOD using like DDR data, and I actually use a 90-degree out of phase clock to do that, generated by the PLL. And so the I/O that's generating the clock signal to the UP75 panels isn't actually clocked from the same clock as the data bits. It's clocked by a clock that's slightly late, well, 90-degree out of phase, right? Yeah, that would be a possibility, but both of those are slightly more complicated, and they depend on more specialized resource in the FPGA that might not be available. And like in the iCE40 here, in this example, I'm trying not to use them for this case, because in this case I don't have to, and I need those features for something else that I want at the same time in the design. Yeah, so that was the output data, which is the very simple case. Now we have to worry about input. And let me tell you, input is way more annoying. So let's look first at what do we have, like from an input standpoint. Let's look at the data sheet of the chip. So this one is slightly more clear. I can actually put it full screen again. So serial output timing. Okay. So the first thing to note is that the flash chip is gonna output data on the clock falling edge, like the SPI clock falling edge. It will output data sometimes after. And so just like in the opposite case, you have what's called a TCLQV and TCLQX. So one is like the minimum clock to out, and the other is the actual clock to out, right? So if we look at those values, TCLQV and TCLQX. So they call them the output all time, which is like the minimum clock to out, or yeah. And it's 2 nanoseconds, and the clock low to output valid, which is the clock to out, is 7 nanoseconds. Okay, let's try to find those values for the PSRAM. Output hold from clock falling is 1.5 nanoseconds, so it's shorter, right? Yeah, so it maintains its data less, only 1.5 nanoseconds. And the clock falling to output value is 7 nanoseconds, and that's the same, okay. So let's take 1 and 7 as value. That will cover both at once. So let's go and draw that. Data in. So we said that it shows up 1 nanosecond after. So 1 nanosecond after the SPI. So now we're obviously the SPI flash has no idea of the clock inside the FPGA, right? All the values of the data sheet are relative to the SPI clock that it sees itself, right? So you have like a dual layer because the phase of that clock depends on that delay, and that's the only edge we can reference input timing to. So 1 nanosecond after, the data becomes invalid. So that would be 1 nanosecond. So at that point it becomes basically garbage. And then 7 nanoseconds afterward, 1, 2, so something like around here. I mean, it's not perfectly to scale. I can't draw perfectly to scale. So that's just garbage. And so the next one would be somewhere around here, right? Okay, that's no, that's not correct. Seven is that delay? Hey, hi to 86 Tech. Welcome to the stream. So that little chunk is the only place where the data from the flash is guaranteed to be valid, and that's the only place we can rely on it being there, and that's where we need to capture it if we want our design to actually work, 100% of the time, no matter what batch of flash chip we got or stuff like that. Obviously, the data is not, garbage there. It becomes valid at some point somewhere there, but if we can't rely on it being there, so we need to capture it during that small interval of time. And so that interval of time is is 4 nanosecond wide. So out of our 10 nanosecond clock period, we have a data valid window of 4 nanosecond, and we need to somehow fit. If we look back at our little cheat sheet here, we have a setup time of 3 nanoseconds. So we need to fit a 3 nanosecond setup window inside a 4 nanosecond valid window to be guaranteed that the capture from the flash chip is going to work. That's actually that could be worse. It's not ideal, obviously, because we have a whole nanoseconds of margin, right? But that could definitely be worse. So let's see what we can do about that. Okay, I'm just checking my drawing to make sure I haven't aligned stuff by accident, because I don't think this edge is especially aligned to that one. That's just a drawing error, I think. Yeah, it's sort of a drawing error. This edge isn't especially aligned to that one. I have no idea of the relationship between that edge and that edge. That's like a accident, I'm gonna say. So we know. Well, I mean, we can sample data. So if we draw our input flip-flop, just gonna increase the size of my FPGA here. We have our output flip-flop. Obviously, if we sample on the rising edge of our input flip-flop here, we're just gonna sample garbage, right? The setup window is 4 nanoseconds that way. Well, no, sorry, 3 nanoseconds that way. So if we use this edge, that has absolutely no chance whatsoever of working. So we can just forget about that edge. So let's try sampling on the falling edge of our FPGA clock, which is this edge. That means that our sampling window would be well, let me change that, because I'm just annoyed that this is sort of aligned with this, which is, it's not really. I'm gonna try to see if I can change that. Shift it slightly. Yeah. So it's less aligned. Okay, so it's more clear that these aren't aligned. Okay, something like this. So that edge. So our capture window would start 3 nanoseconds in this direction, which would be somewhere around here, and we have a hold time of minus 0.4 nanoseconds. That means that instead of having to maintain the data after this edge, we can actually stop it before it. That's the meaning of a negative hold time, which means the data actually needs to be stopped needing to be valid somewhere around here. So that would be our capture window if we use the falling edge of the clock. Now the question is, does that work or not? So here we have 0.4, and this is 3 nanoseconds. So the question now is, does this fall inside of this? Because yeah, on my drawing it might work, but my drawing isn't to scale, so we actually need to check using the actual number. So here we have 3 nanoseconds, then we have 7 nanoseconds, so that's 10, right, from here to here. Which means that this is pretty much aligned with this. So that means that this window of 4 nanoseconds starts aligned with that edge. And then we have it for 4 nanoseconds. Okay. So I don't know if you're following, but okay. So between here and here, we have 10 nanoseconds because we have 3 nanoseconds here to go from that edge to that edge, and then we have 7 nanoseconds to go from this to this edge. So from there to there, we have 10 nanoseconds by the numbers. That's where our data valid window starts. And then from here, so that means that it's aligned with this edge. Now, obviously, because this is half a clock cycle, this is 5 nanoseconds, right? That's half of 10, right? Which means that essentially our data window starts here and ends 1 nanoseconds before here. So we meet this, we meet the 3 nanosecond setup time, but we actually miss the 0.4 number because our data becomes invalid 1 nanoseconds beforehand and not 0.4. Now, I don't know if you remember the datasheet. I mean, that was like not so long ago. It was like 10 minutes ago. But I kind of rounded down the 1.5 nanoseconds to 1 nanosecond because I figured that wouldn't make that much of a difference. But it turns out that it actually does. Like if we take the real number of 1.5 nanoseconds here, that would mean that this number would be 1.5 nanoseconds, and this window here would be 4.5 nanoseconds. And at that point, we actually just barely miss timing by 100 picoseconds. If you miss timing by 100 picoseconds, don't worry about it because these are just typical numbers and average and so in this particular example, it turns out that sampling on the falling edge probably will work and probably will work reliably. Because I mean, you know, all of these, they kind of, I mean, some of them are worst case, like the data from the flash, they're worst case, right? So it's gonna be slightly larger than that. So I have full confidence that for the flash running at 100 megahertz, using those timings, it's gonna work, right? Hopefully, though, you can see the issue is that we only had two options. We could sample on the rising edge, or we could sample on the falling edge. And you kind of have to hope that one of the two works. And here it does. Like if we sample on the falling edge, that works. But sometimes it might not, right? Also notice that we sample on the falling edge, but that's like this rising edge triggered the output of that bit, and we sample it not on the falling edge that follow. We have to sample it on one cycle later. So this entire thing had more than one clock cycle of latency, which is something you need to obviously take into account in your design. Is that sometimes the whole latency of the I/O pipeline from the output register to the device, then back to the input register, you can actually easily have 3 cycles of latency. You have the passing the first clock, then actually the device responding to your clock edge, and then one which adds one more cycle, and then actually sampling it in the I/O register. You only get kind of the response from the device 3 cycles after, which in the case of SPI we don't care because we read data. We just need to capture it a little later. There's no loop or feedback or something like that requirement, so that's not of an issue. But if you want an example of where that matters, you can look at the Glasgow interface, like the Glasgow interfaces to the FX2. There's obviously an interface between the two that needs to communicate, you know, outside the FPGA to the FX2. The FX2 has some clock to out, some setup time, some hold time requirements, stuff like that. And so we actually made an analysis exactly like this to see if it would meet timing or not. And it has latency. And the problem is one of the bits that the FX2 feedbacks is it's a bit that says if the FIFO is full or not. And that's kind of a problem if you have a 3-cycle latency, right? Because you only find out if the FIFO has become full 2 cycles too late, basically. And so that was kind of a big problem that needed to be solved and stuff like that. You can look at the details and the timing analysis in the issue on GitHub. But yeah, sometimes latency is definitely an issue. Is there a difference in sampling on the rising or the falling edge? So it has to do with the delay. Well, I mean, here is obviously a 5 nanosecond difference, like between sampling on the rising and the falling edge, right? And yeah, we need to sample on the falling edge so that or capture window, which is where the data is going to be sampled from, actually falls inside the data valid window from the SPI flash. If you were to use the SPI, would you still need to register? Yes, you would. Because if you don't use the I/O buffer, if you don't use the I/O registers, you have no clue whatsoever of the kind of delay you'll have between the input of your clock, the internal version of your clock, and the external version of your clock, if you wish. I mean, sure, you can control it, but you have no idea what it is. So you would still use a DDR output flip-flop with, except here you would have like 1 and 0 instead of 0 and 1, for instance. But yeah, to output clock, if you want that clock to have a known phase relationship to the output data, you should use an I/O register. Now, because the clock is most likely to use a global buffers, chances are that you could So in some FPGA, I think at least the old Xilinx, I don't know about the new one, but they had a dedicated path to output a clock as well. So there is a dedicated path to input a clock. They also had a dedicated path to output a clock, which provided a known phase relationship. Now, that known phase relationship wasn't the same as the one if you used an I/O register, right? It would have been a different phase, which you would need to analyze using the tool. Like as I said, in the ECP5 as well, the open tools don't provide any kind of data, but you could use Diamond for the ECP5. You could use Diamond to see if. Actually, you know what? I don't know if it provides it or not. That's something that would need to be tested basically in the in Diamond or not. But it might be variable, because I don't think the FPGA architecture itself has any dedicated path to go from the global clock network to that wire, essentially. So it would have to use like normal fabric resources, like the normal routing. And the problem in the normal routing is that you have different types of routing resources. And so depending on what the router decided to use that day to route your clock, you could potentially have variable delays, which would not be good. Like to input a clock from the outside to the FPGA, Diamond will actually refuse your design if you're not using a dedicated input clock pad, like a clock pad that's been designated as a global clock input. Technically, you can input the clock and the open tools will let you do that, but because it's using random fabric resources to route that clock, the delay is basically random. You have no idea what it is. And so guaranteeing any kind of phase relationship between that and other things is impossible, and so Diamond just forbids it altogether. That's for input clocks. For output clocks, I'm not entirely sure, but I would definitely still, using I/O register is the best way to make sure that you have a known phase relationship between the clock and your data, and then using the I/O delays, you would use that. If you're using a synchronized with, it's a way to run a shift without using a PLR. Oh, here's the answer, just to resolve it. Okay, so you mean if instead of generating the clock, you have something like the clock is generated outside and you have some data that comes with it. Is that what you were asking about? Okay, I'm not familiar with the STM memory bus, but same idea, I'm guessing. Well, you have several consideration with that. Let me actually draw that bigger because it's gonna take some. So that's your data bus, and it goes to an IO flip-flop, right? And you need to somehow sample it at the right time, and you have the clock that goes and clock that flip-flop, and possibly clock other resources inside the FPGA, whatever. Now, the problem with that, I mean, it's not a problem, it's a hey, hi, GKIV? JKIV? The problem is the delay from this to the input of the flip-flop is not the same as the delay from here to there. This pass is going to take way more time because this goes from the pad to the IO that's like right next to it in the IO block, while this path is gonna go to through the input buffer of another IO block. Then it's gonna need to go through the global clock buffer, and then it's gonna need to be distributed all around the FPGA, which means that the clock signal is gonna take way longer to arrive. So if you draw this, let me actually draw the let's say that that's your bus clock. And let's say that that's your data. I'm assuming it's single data rate and it's transitioning at the same time as the clock. Right? So that's on the outside. Now, on the inside of the FPGA, this is going to be shifted by some unknown amount. Like I have no idea the delay of the FPGA in particular or whatever. But that's the data inside at, actually let me zoom, yeah. That's the data inside the FPGA right at the input of that flip-flop, like just right there, okay? Now the problem is because the clock has a way longer path to go because it needs to go through the same input buffer, but instead of going to the clock input directly in the same IO cell, it has to go through the entire clock distribution network. The bus clock here is gonna be way later. So it might be like here. Now, I need to. Now, in that diagram, yes, exactly. That's what I was coming at. Is that at least in the ECP5, that's something that's like, because I actually had the case for AGMII, is that you have this case here, basically, and the clock delay. I don't remember the. I don't remember the numbers, but it's substantial. Like it's like 4 nanoseconds or 3 or 4 nanoseconds or something, which is basically enough to meet the setup time of this. And so you don't actually need to delay anything. You can just capture the data as is with the rising edge, and meet the timing. Like if I go back to that. Sorry. Where do I have it? Oh, that's this thing. If I go back to this, that number here, that's the number I have here. FPGA IO 4 nanoseconds. That's the time it takes for the clock inside the FPGA, the clock pad outside the here, to go all the way through to that clock input of the IO register of the FPGA. It takes 4 nanoseconds. And so, because your setup time is only 3 nanoseconds, turns out that it just works. You don't have to do anything. And you can guarantee your timing statically just by design of the FPGA, essentially. Which turns out is very convenient. So yeah, I hope that answered your question. I don't know what your target FPGA is. I don't have the numbers for the ECP5 here. You'd have to check Diamond. I haven't made a cheat sheet yet for Diamond yet. No, that's really nice. Is that the additional delay of the clock input turns out to meet the requirement of the FPGA, independent of the bus frequency. I mean, as long as you don't go too fast to not actually meet the setup time at all. But and that's definitely very nice that it just happened to work. Yeah. But alternatively, if it turns out that it doesn't because of this or this reasons, again, you can play with input and output delays. Like the iCE40 doesn't have any of this, right? But in the ECP5, again, at this point here, I mean here and here, you can have programmable delays that you can use to adjust your margins if you find they're not good enough. And alternatively, again, if your bus is a single data rate and the positive edge doesn't work, and you wanted, like you were talking about a 180-degree phase shift, like if one of the edge doesn't work, you can use the negative edge instead, and then you get your 180-degree phase shift by just using the falling edge instead of the rising edge. Then you don't need a PLL. And then of course there is like the bazooka option, you can use a PLL, and then you have like infinitely variable phase shift to place it wherever you want in the relative to your bus clock. But that kind of assumes also that your bus clock is free running, right? Which is not always the case for all buses. Like I'm assuming in the STM32 memory bus it is a free running clock, but if you were trying to sample like a QSPI bus or something being a SPI slave, the clock is not free running, so you can't lock a PLL to it or anything like that. Okay, so going back to that example, so it was nice that it just worked, right? Now, the fact that it worked at 100 megahertz say absolutely nothing if it's gonna work at any other frequency. Like just because it works at 100 megahertz doesn't mean it's gonna work even at 80 megahertz or 60 megahertz or stuff like that, because those timing are all interdependent and they kind of shift one next to the other. And so you might find that at lower frequency, instead of using that falling edge, you need to use that rising edge, for instance. And you need, if you change the frequency of operation of your core, you might need to change which edge you use. Now, we were also lucky that it just so happened that it worked. It might not always be the case. It might be that neither this one or this one actually meet the requirement, and that so none of the edge that you have available are an option at all. And that's kind of where we get in the same domain as this. Is you have several options. The first one is just like some FPGA have programmable output delay between the IO register and the actual pad. Well, you have that the other way around as well. You can delay the data from the pad to the IO register through a programmable delay. Again, not an option in the iCE40, but on the ECP5, on Xilinx 7 series, that definitely exists, and that's a perfectly valid option to use. Now, for input timing, you can also influence them using output delays, somewhat counterintuitively, but as you see, all the data output from the flash, they're relative to the SPI clock, and the SPI clock is controlled by us, right? Which means we can apply an output delay on the SPI clock output that we generate to shift the output from the flash somewhere that we can capture. That's another option. And finally, the other option, the kind of the final option, if you don't have IO delays and you can't shift your output clock timing, is to use a different clock for capturing data. Like if we go back to the IO diagram from Lattice, so that's this one, I think. Yes, that's the one I was looking for originally. The clock used for outputting data, so for the output flip-flops, and the clock used for the input is actually different, which means we can sample data using a different clock, and the FPGA PLL can potentially generate for us a different clock. If we look, there's a diagram of the PLL here. That's okay. Actually, can I close this thing? Here. Okay. So that's the diagram of the PLL according to Lattice. It's lying. Yeah, interacting with three-state buses is always fun. Thankfully, most of the time the data is it's what you need to three-state, and so you try to keep that aligned, the output data at least, so you can control it more easily. But yeah, I mean, most of the buses have like a transition, like a 1 bit during which you can transition the bus to avoid contention. But yeah, that's definitely something to pay attention to. So that's the diagram from Lattice for the PLL, and it's not correct. Or rather, it's lying. So I'm just going to try to draw quickly the real PLL output blocks. So you have kind of the PLL core, and that generates a given frequency, right? Now, that frequency can optionally go through a divide by 2 block. So divide by 2 block. And then it can go through another block, which is a divide by n, 0, 90, and n can be 4, 5, or 7. And in addition to dividing by the frequency by 4, 5, or 7, it also outputs 2 versions of the clock, which is a 90-degree phase and a 0-degree phase and a 90-degree phase. So that's the first thing that's not really, I mean, you have the phase shifter, that's kind of the divider. So this block, the phase shifter that's in the diagram that I highlighted, is this thing here. But the diagram doesn't show the divide by 2, but it exists, right? And the other thing that this diagram doesn't show is that you actually have 2 outputs. And each of them can be independently configured to any of those 4 clock options. So we have something like then and so that would be the B output. And the A output has a delay, which is programmable between 0 and roughly 2 nanoseconds. That's the A output. So that's how the PLL really works. And contrary to what it says in the datasheet, you can use the fine delay adjustment without using the phase shifter, and only the A output is delayed and not the B output. And so you can easily generate like let's say your main system clock with the B output, and then use the A output to capture your input data. And that delay is programmable, which means if we come back to our diagram here, you could essentially move this window, like 2 nanoseconds one way or 2 nanoseconds the other way. And between that and the fact that you can select which edge you want to use, you should be able to find somewhere valid to capture your input data, hopefully. Now, as I mentioned, okay, I won't have the time because it's already actually way longer than I thought it would take. But I'm just quickly gonna present the problem with HyperRAM and show you how it's solved essentially using that phase shift. So if we open the datasheet for HyperRAM chip, so let me go here and find a datasheet for HyperRAM chip. Yes. So the first issue is that HyperRAM is double data rate. So we need to capture data both on the rising and the falling edge. So we can't use that kind of trick to shift our data around, to shift or capture window around, because we already need to use both edges. And the other problem is if we scroll down to the timing, okay, so that's the IO. Where are the AC test conditions? Okay, yeah, that's sort of it. So let's imagine that we're trying to run it at 100 megahertz. So let me actually just do this. So these are all our IO timing for the chip. And let's look at, compared to the clock, when is the data valid? So that's our clock. I'm just 1, 2, 3. So the data becomes valid. Wait, no, a clock transition to DQ valid here. It can be as late as 5.5 nanoseconds. So that means that this edge would trigger data that can potentially only become valid here. And then we have a CQ, right? Something like this. Which is, in the worst case scenario, it takes 6 nanoseconds to become valid. I mean, that's the guaranteed timing. Or 5.5, depending on which chip, but it doesn't change much. And it becomes invalid a minimum of 0 nanoseconds after the clock edge. So it becomes invalid starting from here. So it becomes invalid before potentially it becomes valid, which means our data valid window is negative, right? So there is absolutely no time whatsoever on the bus where you can be guaranteed that the data is there. So are you supposed to use this? Well, you're basically not supposed to use it statically, I'm gonna say. By design, you have to use retraining, because those delays, they don't vary cycle to cycle, they will vary device to device. But one device itself is going to be pretty stable. I mean, given it doesn't change temperature and stuff like that, the delay is not going to be 6 nanoseconds. It's going to be like 3 nanoseconds, and the invalid delay is not going to be 0. It's going to be somewhere between 0 and 4.3. And you're guaranteed to have at least a 3.3 nanosecond valid window. But you have absolutely no clue whatsoever of where that window is. Could be there. Could be there. You don't know. And so for that kind of device, you essentially have the same thing for DDR and DDR3 and stuff like that. All fast memory bus. You're guaranteed a certain data valid window. You just have absolutely no idea where it is. And that's where you need to use memory training. Because the right timing just like in SPI, are kind of guaranteed to work by design, because you generate the clock, so you're kind of the master, so you can guarantee that they work. You can guarantee the input, the setup, and all time for the write commands. So what you do is that you write at boot. You write some word in memory, some pattern somewhere in memory, and then you try to read it. And you use the PLL. I mean, at least that's what I do in the iCE40 IPRM controller, is that I'm using that delay to sort of find where the data valid window is. So you write a certain a given pattern in memory, and then you basically try all possible delay values until you find one that works. That's pretty much how our memory training works. Now, you can do this by varying the phase of your capture clock, or alternatively, again, if you are in an ECP5, what you would typically do is you have your input buffer, and then you have your input delay. And all those blocks, they actually allow you to, the value isn't static. You can change it at runtime to increment and decrementing, and you try a bunch of values until you actually find one that works. And so between trying different delay values, trying both the rising and the falling edge, and the answer is technically no. If you want to meet the spec, it's not enough. But between the 2 nanosecond value and switching between the 0 degree phase of the clock and the 90 degree phase of the clock, I can find one value that works. But yeah, technically 2 nanoseconds is not necessarily enough. But because you are guaranteed a 3 nanoseconds or nearly a 4 nanoseconds valid window, and you have a 5 nanosecond period, like 2 nanoseconds just allows you just enough to manage to place it somewhere it works. Basically, I mean, the 2 nanosecond windows plus the fact that you can switch between 0 and 90 degree phase of your clock. It's like the combination of the two thing. But on an ECP5, like with the I delay, I think the I delay has more range than 2 nanoseconds. I don't remember, because it has 64 possible value. Each of them is 150 picosecond tap, I think. I mean, I wish. Yeah, it says I'd have to return, but the I delay has more range than 2 nanoseconds. So on the ECP5, you guarantee to find a value that works. On the iCE40, it's definitely oh no, the iCE40 was definitely not designed with that in mind. I mean, I'm definitely abusing it for things it was not designed for. there's absolutely no doubt about it. I mean, when you look at the fabric, it's not designed to run stuff at 100 megahertz, 200 megahertz DDR, stuff like that. That's no, it's a low. It's an at least the iCE40 Ultra, the UL5K, which I'm targeting, is meant for ultra low power. It's not meant for speed at all. So yeah. I think I'm just gonna stop here because I won't have the time to get into like high speed SerDes and how I coded them on the iCE40 in like 15 minutes to keep the stream to 2 hours. So yeah, just increase the supply voltage. I mean, I did. I think what I've shown the graph, right, of the running the iCE40 at 1.35 volt or 1.4 volt, seeing the speed increase and stuff like that. And I mean, all the timings that I listed here, they're kind of like typical or worst case timings, but you can actually get better. Like I think in the best case, the setup time is not 3 nanoseconds; it's more like 2 nanoseconds. And same thing for the hyperram time, the hyperram datasheet. These are the worst case timings, right? So most of the time, the capture window is going to be larger than this, so you have more margin than you think. And so I haven't. Of course, my sample size is relatively small, but I did always manage to find a capture window with a very, very wide margin of value that works. I think I'm going to stop my explanation here, but if anybody has a question or stuff in particular that they would like explain or something. I guess Peter had raised something yesterday, which is how I implemented the fast. So if you go to so I did implement SPI slave core and like a fast version, and this one. Oh wow! I documented it. I didn't even remember I did that. This one allows to go way faster because it uses the SPI clock itself to clock the shift register of the SPI, right? And in that core, I had to manually, like if you look at the actual source code, there are things like that, where I basically hard-coded some of the resources at some specific site inside the FPGA to guarantee that I would meet timing. I have some LUTs that are locked into specific places in the FPGA for several things. And I had to do that for several reasons. Wait, does that work? Yeah. No, never mind. I forget about something. So the question was, why did I have to do that? Well, there are two reasons. The first is I'm crossing clock domains, right? Because I'm passing data from the SPI clock domain to my system clock domain. And currently Next PNR does not allow a user to constrain cross clock domain path. It will analyze the delay and tell you the delay, but it can't guarantee anything, and it won't check or try to make them as short as possible or any of that stuff. And here that would be a problem because I want to guarantee that if I have like a bus of, you know, 8-bit bus that's clocked by the SPI clock, and then I want to sample it in my system clock domain, I want those 8 sample bits to kind of be sampled at the same time. Hey, hi George. Yeah, no problem. Glad you could join us, and yeah, see you on Discord anyway. Bye. So I want my 8 bits to be sampled at the same time and somewhat coherently. So I want to minimize the delay between those two flip-flops. And so what I do in the FPGA is that I constrain them to be on adjacent tile, like right next to each other, basically. And unfortunately, there is no other way in NextPNR than to manually log them to a given cell. So that's what I've done. And the other reason that I had to do that is because in that design, I couldn't use the IO registers. Like, you know, I just spent like 1 hour and 45 minutes explaining why you should always use the IO registers. And here I don't. And that's because the IO registers don't have some of the features that the internal registers have. And so there was just no way for me to use the IO registers, which means I had to take the data from the IO through the fabric and register them inside the FPGA, right? And the only way I could guarantee that this design would be stable and work all the time and work reliably, independently of the random seed that NextPNR choose and whatever placement it made, is to make sure that all my input and output registers are locked at a specific site inside the FPGA that doesn't move relative to the IO. And I also put them in tiles which are right next to the IO tile to minimize the delay and stuff like that, and make sure it's not random depending on the build. And for it, that means that that block pretty much only works when you use the specific pins that, well, I used for the SPI. I hope, Peter, that that kind of answered your question about why I had to do that. And so, yeah, among other things, I also locked like the input global buffer so that the clock delay is between the external version of the SPI clock and the internal SPI clock is also fixed and stuff like that. So does anybody have any question before I finish? I hope that was hopefully interesting or instructive, and that you will you know, at least have an idea of how to do timing analysis and how to look at IO timings when you need to interface stuff at to various external devices at non-trivial speed. Oh wow! I'm sorry, I don't have like a fancy things like Peter that spawns all the follow, but I see quite a few people have followed me. So thank you all for the follow. Well, okay, well, glad I could help then. Okay, if there are no further questions, I think I'm just gonna finish here. And if you need any recommendation, I think Sion from Unexpected Maker streams in like 30 minutes or something on YouTube. So some other interesting content if you're looking for something to watch. Okay, guys. Again, if you want to, I will post this video on YouTube, on my YouTube channel, if you need to refer to it later on or something. It will be available there. It should also be available on Twitch as a highlight. And you can find me on ISC and on the Open FPGA channel under the name TNT. And you can also find me on Twitter under TNT and on the 1-Bit Squared Discord. So yeah, there shouldn't be no problem reaching me. Okay, see you guys, bye.